we're going to get back to the blood pressure side of things. These last two videos have to do with blood pressure regulation. Okay, so not just how the relationship with pressure and flow and all that, but just blood pressure regulation. So we've got a couple of different reflexes that help us with blood pressure. So to start off, if we're going to have a reflex, we need to have a receptor to know what's going on. And so we have these baroreceptors. They're basically mechanoreceptors that respond, that are specific to or respond to changes in pressure. Okay. And what happens is the pressure increases, they stretch out. And when they stretch out, because of increased pressure, they let the brain know by sending more action potentials. However, if pressure is low, the number of action potentials that's sent out is reduced. And so that's how our brain interprets. So the baroreceptor reflex is just change in blood pressure will cause other changes. Okay, or we're going to have a response here. So we're in this flow chart here, which you might screen grab or whatever. I'm not going to really focus on it. But if we've got increased blood pressure, we're going to have high firing rate of the baroreceptors. That's going to go to the brain, and the brain's going to go, hey, I want to lower pressure. I'm going to ultimately create a negative feedback loop. Okay. Now, this shouldn't be, especially if you're watching this after you've had the week 8 and or week 9 lab, this should make sense. At least be familiar. Okay, so let's just say that I've got low blood pressure. So that's decreased stretch. So fewer action potentials go to my brain. And as a result, I've got low pressure, so I want to increase pressure. So because I've got low pressure, the goal or the job is going to be now to increase mean arterial pressure. Okay? And so we do this a couple of ways. One, we mess with the parasympathetic nervous system, and then we also mess with the sympathetic nervous system. So we decrease parasympathetic tone or activity. We call this parasympathetic withdrawal when we decrease the activity. And so as a result, we release less acetylcholine out of the SA node, so we're not activating those muscarinic cholinergic receptors. Okay? What does this do? This leads to an increase in heart rate. Okay, remember, parasympathetic activity reduces heart rate, but if I'm reducing parasympathetic tone, I'm going to have higher heart rate. The sympathetic nervous system, on the other hand, releases epi and norepi. And unlike the parasympathetic side, which just deals with heart rate, epi and norepi, or the sympathetic nervous system, affects heart rate, stroke volume, and resistance. Okay, so here are our 3 effects over on the right here. All 3 of them have adrenergic receptors. The 2 on the heart are beta. The 1 on the arterioles is alpha. A is for alpha. A is for arterioles. And the result is we're going to increase the firing rate. So we release norepinephrine onto the SA node. That increases the firing rate. I release norepinephrine onto the ventricles. That increases the contraction strength. Okay. I release epinephrine onto the arterioles. That causes vasoconstriction. As a result, mean arterial pressure increases. Okay, remember that mean arterial pressure equals heart rate times stroke volume times resistance. So we increase any and all of those variables, we're going to increase pressure. All right, then we've got the chemoreceptor reflex. Has nothing to do, the stimulus is not pressure. The stimulus is down here. So either we've got high CO2, low pH, which means we have high hydrogen ion, or low oxygen. We're trying to get back to homeostasis. So these chemoreceptors that sense this, also they're in the medulla and they're in the carotid sinus. They send signals to the brain. Brain goes, oh, I've got low oxygen, high CO2, high hydrogen ion. We're going to do some things differently. So one of the things that happens is we increase our breathing. Okay. What also happens is we increase blood pressure, and ultimately we get back to homeostasis. Okay, with low oxygen, we can compensate for that by having an increased cardiac output. Okay, there might be less oxygen, but if I'm working harder, my heart's working harder, delivering more blood, I might be able to compensate for that. Okay, so just put this in words. Chemoreceptors sense that low oxygen, high CO2, and or high hydrogen ion. Okay, the chemoreceptors tell that to the medulla. And as a result, we increase cardiac output, resistance, and pressure. And in the respiratory system, we increase respiratory rate to reach homeostasis.